I'd like to take a few minutes to do a quick overview of section 1.5 on limits. Remember, in Blackboard and in emails I've sent you, there are lots of other resources you can use, but I do want to begin with an overview. Consider this function. The graph is drawn for you, but it's the function f of x equals x squared plus 1. We're going to introduce the notation and the idea of a limit of a function. And I'm going to start off with the notation. This symbology there means LIM is read the limit of whatever's in front of that, which in this case is x squared plus 1. So you have the limit of x squared plus 1, and then the part below the LIM is read as x approaches. The arrow is approaches, so as x approaches the number 1. So again, that symbology is read the limit of f of x plus, the limit of x squared plus 1 as x approaches 1. So here you're going to be learning the symbols and how to interpret them as much as you are the concepts, at least in the beginning. But what I want to do is look at what happens to the values of this function f of x as x gets closer and closer to 1. And I'm going to begin doing that by making a little table of x and y values, or x and f of x values. So across the first row, I have x taking on different values, increasing closer to 1 from the smaller side of 1, in other words, from the left of 1. So I take 0.9, get a little bit closer, 0.99, get a little bit closer yet, 0.999, getting closer and closer to 1 from the left. And you can see as I move from 0.9 to 0.99 to 0.999, that f of x values go from about 1.810 to 1.9801 to 1.9988001, seemingly getting closer and closer to 2. So as x gets closer and closer to 1 from the left side of 1, the y values, or the f of x values, the function values, are getting closer and closer to the number 2. Now if I come in from the right side of 1, in other words, numbers slightly bigger than 1 but increasingly closer to 1, for instance, going to the far right, if I take x to be 1.1 and then move one step to the left, I get 1.01, and then move again, I get 1.001. And you can see that those y values, or the function values, reading from right to left, go from 2.21 to 2.0201 to 2.002, increasingly closer to the number 2. So as you can see, from the left or from the right, and we're going to call those left-hand and right-hand limits. And they're the same thing in this case. So if you come in toward 1 from the left side of 1, the function value gets closer and closer to 2. And as you come in from the right side of 1, but increasingly closer to 1, the function values also approach 2. Whenever those left and right-hand limits agree with each other, we say that the limit itself exists. You could call it a two-sided limit if you wanted to, but typically you just call it the limit. The limit itself is equal to 2, as long as you get the same answer coming in from the left side and the right side. So in terms of just the mechanics and reading the symbols, this is the kind of stuff you'll need to know to be able to do your homework from section 1.5. Now, what happens if you get, say, closer and closer to 2 from the left, but maybe you got closer and closer to 5 from the right? If that were to happen, if the left and right hand limits did not agree with each other, you would just say the limit does not exist. And for this course, a lot of times the homework will tell you to type in DNE for does not exist. And that happens when the left side limit and the right side limit, or what we'll call the left hand and right hand limits, don't equal each other. If they do, you can say the limit exists, and it's whatever that agreed value is. And if they don't, you say the limit does not exist. Now let's go back and look at just the part of the analysis that dealt with the left-hand limit, or the left side. If you look at that, we're going to introduce specific notation just for coming in from the left. And what we're going to do is we're going to take that limit symbology, just like we were using before, but we're going to amend it slightly and put a minus sign as the superscript on the number that x approaches, in this case 1. So if you're doing a left-hand limit, you'll write out the normal limit symbology, but you'll put a superscript of a minus sign on the number that x is approaching. And we call that a left-hand limit. So when you see a limit and you see to the right of the arrow where x is approaching something, if you see a superscript of a negative sign, you'll know that's a left-hand limit. Same thing for the right-hand side. If we come in from the right, we're going to put, I bet you can guess it, we're going to put a superscript plus symbol. And that stands for a right-hand limit. And you can see already that I have a typo. A right-hand limit. So I'm introducing concepts and symbology and terminology all at the same time. But as in most things in mathematics, you learn by doing, and as you work through these problems, it'll become more and more second nature to you. So if we talk about left and right-hand limits together, we call them one-sided limits. So one-sided limits can be left hand or right hand. Now let's look at these limits on the graph itself. We talked about from a strictly algebraic symbol point of view. Now let's look at what this how this interpretation works on the graph itself. If I want to look at a left-hand limit, you notice that minus sign as a superscript. I'm coming in from the left, and I'm getting closer and closer to the number 1. So I'll put 1 down here. I'm coming in from the left. That means I'm coming in from this direction, getting closer and closer. Well, what happens on the curve itself? Well, as I get closer and closer to 1, if you think of a point moving along the curve, it's getting closer and closer to right along in there, which if you think about it, is about 2. And you can see that matches what we knew the answer was from algebraic analysis earlier. So if you look at it graphically, as the x value moves along the x-axis closer and closer to the number that x approaches from whichever direction you ask about, in this case the left, you look at what happens on the curve and see what the y value is being approached, and in this case is 2. We can do the same thing with the right-hand limit. This time we put the number 1, we're approaching 1, but this time we're approaching from the right. So we're going to be coming in from that direction, getting closer and closer to 1. But now we're looking at what happens on the curve as we get closer and closer to 1 from the right. So we're moving down this way, and we're getting closer and closer. Well, again, you can kind of see you're getting closer and closer to right there, which if you think about it is still the number 2. And that's why we say that the right-hand limit is also equal to 2. And as I explained earlier, if the left-hand and right-hand limits are the same, we can say in general that the limit without a superscript, the limit itself, or the two-sided limit of the function as x approaches 1 itself is 2. So the left-hand limit indicates what happens as x gets closer to the value that we're given here, which in the case is 1, but it's from the left. And when we're doing it from the right, we're moving in from numbers greater than 1, but getting closer and closer to 1. So the left side limit, right side limit, and if the two values are equal, that just becomes the limit itself. If those two values do not equal, we say the limit does not exist. So just sort of a summary page. I'm not going to belabor this, but a left-sided limit means you're approaching the x value from the left. Right-sided limit means you're approaching it from the right. You use the superscript minus or plus to indicate which you're talking about. And the normal limit, or what you might call the two-sided limit, exists only if the left and right-hand limits equal each other. If not, you say the limit itself does not exist. Let's look at this problem where we're given the graph of the function. This is actually a piecewise defined function, and we want to find some limits based on that. Let's start off with this one. Find the limit as x approaches 3 of the function f of x, but we're approaching from the left. That's what the superscript means. That means we're getting closer and closer to 3 on the x-axis, which is here, but we're approaching from the left, so we're coming in this way. To find the function value as x gets close to 3, we're essentially riding along on the curve. So as the x value moves in toward 3 from the left, if you're on the function itself, the graph of the function, you're moving in toward this circle right here, which, as you can see, if you cross-reference back to the y-axis, is 1. So the limit of f of x as x approaches 3 from the left is 1. Maybe I can draw a better 1 than that. How about this one? What if I do it from the right? This time I'm moving in toward 3, but this time I'm coming on the right side of 3. So now I'm moving in from this direction, getting closer to 3. But if I want to stay on the function, the curve, the graph that represents the function, then I'm down here. So I'm moving along this part of the curve, this part of the function, and I'm getting closer and closer. As x gets closer and closer to 3 from the right, I'm riding along on this piece, and I'm getting closer and closer to this value, which is -3. So the limit of f of x as x approaches 3 from the right is -3. Now, what does that imply about the limit itself, or the two-sided limit? As we said earlier, if the left-hand limit and the right-hand limit agree, then we can say the limit is whatever that number is. If they don't, we say that the limit does not exist. Simple enough. How about this one? Consider the function f of x equals x squared minus 6x minus 1, and we want to just complete the table. Now here's your calculator problems on steroids. You've got to do a lot of calculator problems. So you take 0.9 and you plug it in and you do your calculations. I'm not going to repeat them here. I'll assume that you can do that. You'll get about -5.5900. It said to take it to 4 decimal places. And as you keep plugging these numbers in, 0.99, and just do these calculations, again, put in 0.9999, and practice this because it is a skill you need to work on to do some of these homework problems. You'll get about -5.9960. If you move to the other side of 1 and do 1.001, you'll get about -6.040. If you do 1.01, again, you're plugging it into these values and doing those calculations. I'm not going to do them all, but if you're doing 1.01, you do 1.01 squared. You find that value in the calculator. Then you subtract -6 times 1.01, and then you would subtract 1 from that. Not hard, but it is tedious sometimes. You might need to practice it. In any case, if you keep doing all those, you'll end up rounding to 4 decimal places. You'll end up with those values. So this is not hard, but it is something you might want to practice because it's easy to make one keystroke mistake and miss the problem. I'm not going to belabor this, but I'm going to throw up some rules for limits. Most of this I think you'll learn in an intuitive way, but if there is something you ever want to go back and formally look at these rules, I'm just putting it out there for that reason. I'll read through some of these and sort of say what they mean, but mostly I want us to learn through doing, not by memorizing these rules. This first one says if k is a constant, that means it's just a number. So if it's like the number 5, the limit of a number is always that number, no matter what x approaches. In other words, what's the limit of 7 as x approaches 2? Well, 7 doesn't include an x, so 7 is always 7. So the limit of a constant of just a number is just that number. Sort of a derived rule from that is if you have the limit of a number multiplied by a function, all you have to do is deal with the limit of that function and just multiply it by the number. So if you want to take the limit of x as x approaches 7, and somebody else gave you the limit of 3x as x approaches 7, you could still just do the limit of x as x approaches 7 and just multiply it by 3. In other words, a constant factor can just be factored outside of a limit. Rule 2 says if you want to take the limit of two functions added together, you can do each limit separately and just add up the two limits, or subtraction if it's subtract them if it's subtraction. Same thing with a product. If you take the limit of two functions multiplied together, you could just take the limit of each function separately and then multiply those answers together. And it works with division as well. The limit of a fraction is just the limit of the top over the bottom, as long as you don't let the bottom be 0. You can't divide by 0, of course. And this rule we use quite often, but it should be obvious if you understand what limits mean. If you've got a polynomial, p of x, the limit is just what you get by plugging that number c in to the polynomial, because whether you're coming from the left or the right, you're going to get the function value if you have a polynomial. But again, rather than memorizing these rules, I'm putting them there for your reference, but mainly you're going to learn this by doing. And speaking of doing, let's continue. Let's do some of these examples. This one starts off with some information. It says the limit of the function f of x as x approaches 4 is 16, and the limit of g of x as x approaches 4 is 8. So what is the limit of the difference of the two functions? Well, according to what I just said, all you've got to do is take each limit separately and subtract. So the limit of f of x as x approaches 4 is 16, and the limit of g of x as x approaches 4 is 8. So the answer is just going to be 16 minus 8, which is 8. Most of this, like I said, you learn by doing, and as you do it, you'll see how simple it really is. What about the limit of the product? Well, again, it's just the product of the limits. The limit of f of x as x approaches 4 is 16, and you multiply by the limit of g of x as x approaches 4, which is 8, and so you take 16 times 8, and that is, if I can do it right in my head, 8 times 6 is 48, I believe 128. You can double check me with your calculator. And for a quotient, you just take 16 divided by 8, which is 2. And if I ask you to calculate the limit of f of x plus 3 times g of x, all you would do is take the limit for f of x, which comes out to be 16, plus 3 times the value of the limit for g of x, which is 8. So you end up with 16 plus 24, which is 40. So you'll see that those page full of rules that I gave you earlier that look so awful, when you actually apply them, it's just almost just common sense. Here's some more. The limit of this expression x squared plus 2x minus 3. Well, remember that number 5 rule said if you're just taking the limit of a polynomial, all you do is plug the number in. So you're approaching 2, so it would be 2 squared plus 2 times 2 minus 3, which would be 4 plus 4 minus 3, which is 8 minus 3, which is 5. Now how about this one? The limit as the absolute value of x plus 3 divided by 5 approaches 3. Now, you've got to think about this one a minute. It's not a polynomial, so it's not clear that you can just plug it in. We don't have any rule that says you can. So whenever that happens, you don't have any other quicker way to do it. The idea is to do left and right hand limits. So if you think about this, if you're going to say, well, the overall limit is just, if it exists, is going to be the same as what you get if the left and right hand limits agree. So let's do a left and right hand limit on this. If you do a left hand limit on this, you'll be talking about the limit as x approaches 3 from the left of this function, absolute value of x plus 3 over 5. You got to think about a number that's close to 3 but a little bit less than 3. So something like 2.99. Well, if you take 2.99 and add to 3, you get 5.99. Absolute value of 5.99 is 5.99. 5.99 divided by 5 is close to 6 divided by 5. And as you can see, as you get closer and closer to 3 from the left, this top is getting closer and closer to being 3 plus 3, which is 6. The absolute value of 6 is 6, and 6 divided by 5 would be 6/5. So if you think about it, if you come in from the left, no matter how close you get to 3, you're going to get something really, really close to 6/5. If you're coming in from the right, you can do the same analysis. The limit as x approaches 3 from the right of the absolute value of x plus 3 over 5. And you can see you get the same sort of analysis. This time you're getting close to 3, but you're taking numbers bigger than 3. The plus means you're taking numbers slightly bigger than 3. So you're like 3.1, 3.001, 3.0001. And you can see you're getting closer and closer to 6 as well, no matter whether you're coming from the left or right. So you can see that the left and right hand limits are both going to be 6/5. And if that happens, you can say that the overall, or the two-sided limit itself, is 6/5. Had the left and right hand numbers come out different, you would have said the limit does not exist. Now sometimes you can use what you might call a little trick to get these results. Anytime you get a rational expression, and you're used to working with these probably from a previous algebra course, if you can get something to factor and cancel, you can get a much simpler expression to work with. And that's what I'm going to try here. If I look at this as the limit as x approaches 2, and I notice that the numerator is the difference of two squares, x squared minus 1 is the same as x plus 1 times x minus 1. If your algebra skills have gone down a little bit, you might want to review that, over x minus 1. But look what happened. Now the x minus 1's divide out, and you end up with the limit as x approaches 2 of the expression x plus 1. And now that's just a polynomial, and you have rule 5, which says you can just plug in. So if you plug in, you get 2 plus 1, which is equal to 3. You'll find a lot of these are just that simple. The next one is the same, except the limit is not approaching 2 anymore, it's approaching 1. So you can use the same result you got above. You can still factor, and you'll be approaching 1 instead of 2, but everything else is going to be the same. You're going to factor the numerator as x plus 1 times x minus 1. You're going to divide out the x minus 1. You're going to end up with the expression x plus 1 in front of the limit, and now you're plugging in 1 instead of 2. But otherwise, it's the same problem. And yet another one, you sort of see where this is headed. The limit as x approaches -3, and your hope is that you'll get a factorization that allows the x plus 3 to divide out. So I'm going to see if I can actually make that happen. If that's an x plus 3, you got to see if this actually works. I mean, it might not work, but if it does work, that has to be an x. And then you're going to have a 6, so it has to be a 2, and you want it to be a minus 6, so it has to be a minus 2. And if you FOIL that out, you can see that it does work. You'll get an x squared for the first, you'll get an outer of negative 2x, and an inner of positive 3x, which is x, and then 3 times minus 2 is minus 6. So again, your algebra skills are going to come into play here sometimes, especially the ability to do some simple factoring. So in fact, that does factor, as we said. That does let the x minus 3 divide out, and you end up with the limit as x approaches negative 3 of the expression x minus 2. And now you can just plug in the minus 3 minus 2 is minus 5. And practice makes perfect on these things. I've emailed you some links to some little video clips that also give you the same kind of practice and watching someone else do these things, and I would highly recommend that you do that. Watch those clips. How about this? Find the limit if it exists. If the answer does not exist, write D and E. So here, this is similar to the one we've already done. Now, there's no guarantee that this factor and cancel will work, but when you see a rational expression in front of a limit, that is the first thing you want to try. So my thought process is, I see this x plus 1 down here, so I'm immediately going to attempt to make this factor so that there's an x plus 1 up here that will cancel out. Now, you can't just make it work if it doesn't, but the hope is that it does. So if it does work, that's got to be an x, because the x times the x will give you the x squared. Actually, that's not true. It's got to be a 6x. Excuse me. It's got to be a 6x, because you're trying to get a 6x squared. And then, if you're going to get a negative 7 on the end, and you've got a plus 1 over here, then that would have to be a negative 7. And you simply have to go off to the side and FOIL it out and see if it really did work. You can't just assume it's going to work, because they might try to trick you. But you might go off to the side and make sure. If you FOIL it out, you'll get 6x squared. And then the outer is minus 7x. And the inner is plus 6x. And the last is a negative 7 times a positive 1 is negative 7. And negative 7x plus 6x is minus x. So you get 6x squared minus x minus 7. And that's exactly what it was. So that did work. You have to make sure it really does factor, though. You can't just assume that it does. It's got to actually work. But once you see that it does, you can legitimately divide out those x plus 1s. And you end up with the limit as x approaches minus 1 of the expression 6x minus 7. And now you can just plug in your negative 1. So you get 6 times negative 1 minus 7, which is negative 6 minus 7, which is negative 13. Again, practice makes perfect. Okay, how about this one? Again, the same idea. I'm going to try, when I see this rational expression, I'm going to try my factor and cancel technique. Well, down bottom, I've got the difference of two squares. I easily can see that. So I know that I can factor the denominator as x plus 2 times x minus 2. But up top, the problem comes if I try to plug a 2 in here. The reason I can't just plug it in is because it makes this factor here 0. If I try to plug a 2 in here, I get 2 minus 2 is 0. It would work over here. I could plug a 2 in here. I get 2 plus 2 is 4. So it's that x minus 2. That's the factor that I'm hoping will cancel. So again, if my technique is going to work, I need that x minus 2 to cancel. So I'm going to guess that I can get it to cancel out. And if it does cancel out, that means that it had a factor up top of x minus 2. And if it in fact does have a factor up top of x minus 2, and if I want to get an x squared when I multiply it back out, then that would have to be an x. And if I want to get a negative 22 on the end, and I've already got a negative 2 sitting there, that would have to be a positive 11. Now, you can't just stop and say, okay, I'm done. You've got to really make sure it really factored right out. Because I was making some assumptions. I knew what I needed the factorization to be in order for it to give me what I needed. But I have to make sure it really does. So I'll go off to the side and make sure it really does work. So I got x squared, and then I got a plus 11x. and I get a minus 2x, and then I get a minus 22. And then 11 minus 2 is 9. So I get x squared plus 9x minus 22, and that is in fact what I was looking for. So it did work. I was hoping it would, because doing that allows me to cancel out the term, the factor that was problematic. And the reason it was the x minus 2 that I wanted to go away is because that was the one that was giving me trouble if I just tried to plug a 2 in directly. Now that leaves me with the limit as x approaches 2 of the expression x plus 11 divided by x plus 2. And as we learned earlier, the limit of a fraction is just going to be the fraction of the limit. So I can just do each limit separately, and each limit separately is a polynomial. So I can just plug 2 in for x up top and 2 in for x down bottom. And I end up with 13 over 4. I'm saying this over and over again, but it's true. Practice makes perfect. Now this one requires a technique that you probably have done occasionally in an algebra class, but it's going to be particularly useful here when you see a square root in a problem. There are other ways to approach this, but one way to think of this is rationalizing the numerator, because you can't just plug 36 in here because you'll end up dividing by 0. You've got to do something. So one technique when you see radicals sometimes in your past algebra experience is to do something called rationalizing either the denominator or numerator. In this case, it's the numerator. And remember, when you rationalize a binomial expression with a radical in it, you multiply the top and the bottom by something called the conjugate. And the conjugate is what you get by changing the middle sign. Now, if you do that, you have to FOIL out the top. So you get the limit as x approaches 36 of, and I'm going to FOIL it, first, outer, inner, last. So the first is the square root of x times the square root of x, which the square root of x times the square root of x is the square root of x squared, which is just x. Then the outer is going to be a 6 times the square root of x. The inner is going to be a minus 6 times the square root of x. And then the last is going to be the minus 6 times the plus 6 is going to be minus 36. And down bottom, I'm not going to try to multiply that out. I'm just going to write it as a product. You don't really need to multiply it out. But look what happens up top. You get a plus square root of x and a minus square root of x. Those just add to 0. So what you end up with is the limit as x approaches 36 of, up top, x minus 36 over, down bottom, x minus 36 times the quantity square root of x plus 6. Now what happens nicely here is that x minus 36 that was causing the problems when you try to plug it to 36 all of a sudden divides out. So you end up with the limit as x approaches 36 of the expression 1 over the square root of x plus 6. And now you've just got a polynomial over a polynomial, and there's no 0 in the denominator if you just plug in 36. So at this point, I can just plug 36 in, and I get 1 over the quantity square root of 36 plus 6. Square root of 36 is 6, so I end up with 1 over 6 plus 6. So when all is said and done, the limit is 1/12. 1/12. So when you see this problem, when you have a binomial with a radical in one of the terms, just do the multiply by the conjugate trick. Do the algebra, and usually that'll get you through. Make sure that you practice, work problems, allow yourself plenty of time. Don't push the deadlines. Watch videos. I've given you lots of links to videos. use the various buttons in your homework, the watch it buttons, and you've got an Ask the Instructor where you can send me an email. You've got tons of ways of getting help. You've got starting next week, you have the online Zoom tutoring opportunities. You have the in-person tutoring in in our regular classroom in the afternoons, and I've given you those dates in Blackboard and on your syllabus. Please take advantage of those things. Stay on track. Stay ahead if you can. Remember, you get a 10% bonus if you get your homework done within 24 hours early, and get off to a good start.